Now we're going to derive the formula for resistors that are in series. What we would like to do is take a circuit that looks like the one that's drawn here and turn it into a little bit simpler circuit, which I'll draw here. It'll be the voltage of the battery. Keep that. And we'll replace those two resistors with one equivalent resistor. And so what must be that equivalent resistor to match the R1 and R2 that are in series? To do that, we need two things. One is Kirchhoff's voltage law, and one is Kirchhoff's current law. The voltage law says the sum of all the voltages around a closed loop will be 0. And the current law says the sum of all the currents into a given point will be 0. We call that point a node. So in this case, the A up here, that A is a node. And it's not important because the current doesn't split, but it'll help give us the formula we want. So starting with Kirchhoff's voltage law, what we're going to see is that if we go around a loop, and it can be either loop, so we can go around the original circuit loop, or we can go around the new circuit loop. In either case, we're going to have to get all the volts to add up to 0. So in this case, we're going to say that if we start on the equivalent circuit, I'll write the equation out. Voltage of the battery, which we gain, minus I R equivalent equals 0. The minus sign came from the fact that as we go through the resistor, our voltage drops. When we go up through a battery, the voltage is gained. So basically we get voltage of the battery equals I R equivalent. So that looks a lot like our toolbox. Oops. Now what we want to do is do the same thing, Kirchhoff's voltage loop, around the upper condition. So we're going to get voltage of the battery minus I1 R1 minus I2 R2, and that will be equal to 0. Or voltage of the battery equals I1 R1 plus I2 R2. So we'll call this equation number 1, that first loop, and the second loop will be equation number 2. And of course, if we equate number 1 and 2, we'll get I R equivalent equals I1 R1 plus I2 R2. Now, if we just knew what the I's were, we'd have this solved. So, from Kirchhoff's current law, we can get an association for I. So up here on the top diagram, I'm going to put some I's up here. I naught is the I that's coming out of the battery. I1 is going through resistor 1. I2 is going through resistor 2. Well, at node A, you can see that what's going into node A is I1. So if I were to sum up the currents at A, what I'll get is current 1 is going into A, current 2 is coming out of A, it's equal to 0. Therefore, I1 equals I2. And we can carry that logic further and we'll find that it's equal to I naught. That means all the i's that we have here are the same. And because of that, we can now write down what our final equation is. Our final equation will be R equivalent equals R1 plus R2. And if we had an R3 in the same kind of format, or an R4, R5, as long as they're in series, we would get this condition. And so for it to be in series, there's the condition right here. All the i's in each element have to be the same. And if that happens, that all the i's are the same, then the series resistors will just add their total resistance, giving us our total formula for resistors in series. And that'll do it.